Welcome grade 12s, and today we are doing some more grade 11 revision, and we are looking at chemical calculations, which you of course might have learnt as stoichiometry. Okay, it is an important part of your exam at the end of the year, and you are going to be asked calculations. Okay, maybe not as directly as you did in grade 11, but it is going to come in. All right, so what are the things you need to know? Well, first of all, you need to be able to define concepts like concentration, standard solution, what is mole, what is molar volume, what is how many mole, what is Avogadro's number, etc. Okay, you also need to be able to use all the equations that you have done in grade 11, like N equals M over M. The number of moles is the number of particles divided by Avogadro's number. Volume is number of moles times molar volume. Concentration is number of moles over volume, or concentration is mass given over molar mass times volume. Okay, we're going to be looking at some of these today. And you need to be able to balance chemical equations. Okay, I know it's one of those sections that you really struggle with. Please go and get a worksheet from your teacher, ask them nicely, okay, find chemical equations and balance, okay? You cannot do any chemical calculation without a balanced equation, okay? So make sure you get there. So let's dive straight in. Okay, first question. Grade 12s, I apologize, you're not ready, you're doing grade 11 work. Grade 12s, I might now be showing you a way that looks slightly different to what your teachers have taught you. It's okay, it is just a method. Understand the concept, okay? That's what you need to get. That's what we're looking for. So, start with something not too difficult, okay? They say to you, consider the following balanced chemical equation, and we are all very grateful right now because it's really balanced. Yay! Copper plus sulfuric acid gives me copper sulfate, sulfur dioxide, and water. Of course, if I put this into the acids and bases section, I could ask you to write this. I can just say to you, copper reacts with sulfuric acid. What do we get as the products, and balance it and do the equation from there? Okay, absolutely can do that. Calculate the mass. So there's some important information straight away. So calculate the mass of the SO2. There we go. Released if 12,7 grams of copper reacts completely with an excess of sulfuric acid. We love excess. Okay, that means the only two things we need to consider is the copper and the sulfur dioxide. So only two things we need to consider, because the sulfuric acid is in excess. It's not going to determine how much sulfur dioxide we get. The copper will. Okay, and they tell me that the copper reacts completely. So in other words, all of it gets used up. Okay. They want to know mass, so we want to have an answer in grams. Remember, in physics, we use kilograms as our SI unit for mass. In chemistry, we use grams. Okay? So, step one in any of these equations is to have a balanced equation. Okay? Now, I like to write the balanced equation again because it's going to help me a little bit later on. So, we're going to write it down. Okay? Now, in this lesson, grade 12s, I'm going to try really hard to make this legible for you because we've got lots of equations. Not so much explanation, but lots of equations. So we're going to write down the equation. Then the next step, okay, is we are going to write down the mole ratio. Now, this is something I do because it makes it easier. So this reacts as 1 to 2 to 1 to 1 to 2. That should have a 2 in front of it, okay? What's important is I'm actually only using the sulfur dioxide and the copper, okay? Now what we do is we write it down so that we write everything under the copper that we have, and we write everything under the sulfur dioxide when we work with it, okay? So starting with the copper, the only way I can do a calculation like this is to use number of moles. So I need to work out how many moles of copper I am going to be working with. Grade 11s, grade 12s, again, I apologize. You absolutely can write N equals M over M. But you're going to be doing this equation 3, 4, 5 times, maybe, or at least twice. Make sure your examiner knows what you're dealing with, okay? So we're looking at the copper. They told you that it's 12,7. Molar mass, we get straight off the periodic table. We read it off, 63,5, copper and sulfur, chlorine, other ones we have that I've got decimals on it, put it into our calculator, and we get 0.2 moles. Now, from the mole ratio, copper reacts with sulfur dioxide in a 1-to-1 ratio, which means for every mole of copper that I use up, I will create 1 mole of sulfur dioxide. So I need to work out how much sulfur dioxide I'm going to get. So I'm going to take 0.2 and I multiply it by the mole ratio. Now the mole ratio is the 1 from the sulfur dioxide divided by the 1 from the copper. I like to call it a want over got ratio. It's the number of the compound that I want divided by the mole ratio of what I've got, which is the copper. So this is 0.2. But I'm not done. The question said, what is the mass of the sulfur dioxide? That means I need to calculate it. So, mass, number of moles of sulfur dioxide, would be equal to mass divided by molar mass. Okay? So, number of moles is 0.2. Mass is what I'm looking for. But it's sulfur dioxide. So the molar mass of sulfur dioxide, okay, let's just put it over here, means I'm going to take the mass of the sulfur, which is 32, plus, and oxygen is 16, so it's 2 times 16, and 2 times 16 is 32, plus 32 gives me 64. Okay, so this is 64, so mass becomes 0.2 times 64, which is 12.8 grams. Now, it just is a coincidence, grade 12s, that they happen to be very closely related in that I had 12.7 grams of copper and I ended up with 12.8 grams of sulfur dioxide. The only reason being is that sulfur dioxide is only half a gram heavier per mole than copper. Okay, do not take this as being, well, if something's in a 1-to-1 ratio, then I'm going to get the same mass. Not at all. Watch. Let's go to another one just quickly. Same sort of concept, okay? What mass of ammonia gas, okay, that's the 2NH3, will be formed if 112 grams of nitrogen gas reacts with 38 grams of hydrogen to form the ammonia? Assume the reaction goes to completion. Now we've got a problem because I didn't say something was in excess. That means I'm looking for the concept of limiting reactant. Okay? Out of the nitrogen and the hydrogen, something is going to get used up first. Either the nitrogen or the hydrogen, one of them will get used up first. Whichever one gets used up first, that compound or element in this case is the limiting reactant. We need to work that out. So let's do this step by step. First thing, write down the equation again. Okay, so we have N2 plus 3H2 goes to 2NH3. Also, do not assume that because we have so much less hydrogen than we have nitrogen, that the hydrogen is going to be the limiting reactant. Okay, do not make that assumption, particularly because if you look at the mole ratio, I need 3 moles of hydrogen to every 1 mole of nitrogen. Remember, hydrogen is an extremely light gas. So the mass is actually, maybe it isn't the limiting reactant. Maybe it is. We'll have to work it out, okay? And they react in the react 1 to 3 to 2. So for now, I'm looking at the nitrogen and the hydrogen, okay? So let's work out the number of moles of nitrogen. Okay, so we look at this, and they told me at 112 grams. Nitrogen's diatomic. Nitrogen's mass is 14, but there's 2 of them, so it's 28. That gives me 4 moles. Okay, we're okay with that. Working out so far. Number of moles of hydrogen, okay, and it was 38. Mass of hydrogen gas, which is 2 times 1 is 2. That gives me 19 moles. Okay. Can you see that even though the hydrogen was so much smaller in mass, there's actually 19 moles. That's a large amount more. But we still now got to look at this and we go, okay, well, the mole ratio of nitrogen to hydrogen is 1 to 3. That means for every 1 mole of nitrogen, I need 3 moles of hydrogen. So if I have 4 moles of nitrogen, if I times that by 3, I only need 12 moles. I have 19 hydrogens in excess. So the first thing I need to put is, you can either write, therefore, hydrogen is in excess, or you write it like this. The N2 is the limiting reactant. Why is it important to know that N2 is the limiting reactant? Because by knowing that the nitrogen is your limiting reactant, I know that the nitrogen determines how much ammonia I'm going to get. So when I go back here, and now I need to work out how much ammonia I'm going to get, I need to look at the ratio between nitrogen and ammonia. So it's a 1 to 2 ratio. Okay? So that means when I get here, if I now go, the number of moles of ammonia is going to be the 4 moles from the nitrogen times by what I want, which is the ammonia, which was mole ratio of 2, divided by the nitrogen, which was 1. That means I get 8 moles of ammonia. 8 moles. That's a lot. Still not done, though. Question said calculate the mass. So the mass of the ammonia would be the number of moles times the molar mass. Now watch, you can do this in one equation. Okay, last time I did it in 2. It's 8. Ammonia is NH3. Nitrogen has a mass of 14. Hydrogen has a mass of 1. So what this means is actually we have 8 times 17. And of course we use our calculators because they are wonderful, 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 wonderful things. And that gives me 136 grams. Okay, 136 grams. So be careful. Be very, very, very careful, grade 11s, with these. Okay, the first question we did, I told you what was in excess. Easy to then know we've got to use the copper. As soon as I don't tell you that, and I give you 2 values, or I give you 2 amounts of masses, it could have been volume as well, guys, you have to determine the limiting reagent first. Okay? Be very, very careful. So, on that note, I think it is time for a break, and I will see you in a couple of minutes. Welcome back, grade 12s. Okay, so let's dive into the next question. Grade 12s, with this section of work, please do not get freaked out by the question, okay? Because sometimes you're going to see stuff and you go, I've never seen that before. I don't know what it doesn't matter, okay? Deal with it as it comes. So, question says, aluminium sulfate is used as a coagulant in water purification. Now, first of all, if you don't know what coagulant means, it really doesn't matter. But essentially what that means is it makes all the solids come together, okay? It makes it takes all the solids out, essentially, okay? So what happens is it reacts with sodium hydroxide, which we know what that is, to form aluminium hydroxide, which drags the impurities as it settles. So the aluminium sulfate with the sodium hydroxide creates aluminium hydroxide, and the aluminium hydroxide pretty much acts like a magnet and causes all the impurities to attract to it, and then they all go down to the bottom. Okay, so that's pretty much what it means to be a coagulant. Doesn't matter. Now they say to you the balanced equation for the reaction is, first of all, go, oh, balanced equation, yay, yay, very happy, because this one is a mean one to balance. For something like this, they absolutely could ask you for the equation without giving it to you, because they've given you enough information. They tell you that the aluminium sulfate reacts with sodium hydroxide and forms aluminium hydroxide. So what's left has to be the sodium sulfate. It would be so mean if they asked you that, so I don't think they will. Okay? It is balanced. Let's just double check because you never know. All right, let's just double check. Two aluminiums, two aluminiums. Okay, we're happy. 3 times 3 sulfurs, 3 sulfurs. 3 times 4 is 12, plus the 6 oxygens over there, that's 18. Now let's look over here. Well, 3 times 4, that's 12. We got 3, that's 3 oxygens times 2, 6. 18, we're happy. 6 sodiums, 3 times 2, 6 sodiums. Hydrogens, 6 hydrogens. 6 hydrogens, we're happy. It's definitely balanced. Now, a chemist at a water purification plant adds 700 grams of aluminium sulfate to a sample of water. Okay, let's see what he does. Now it says, calculate the maximum mass of the aluminium hydroxide that can be produced. Guys, the fact that we're using the term maximum mass is actually really important because what we're actually working at here is what we call theoretical yield. Theoretical, I think it's an E. Anyway, I'm not going to try to write it down. Theoretical yield. That means if all things being equal, and this being an ideal world where the entire 700 grams of the aluminium sulfate is 100% pure, reacts with the sodium hydroxide and gives me aluminium hydroxide, this is how much I'm going to get. Okay? That's what we mean by maximum yield. Doesn't happen in real life. Okay? We don't often get that, and the percentage yield in a reaction is actually very important. In other words, how much we do actually get out is important, because if it's too low, then in terms of industry, the reaction is a waste of time. Because if the percentage is too low, then why do it? Okay? Because we're just wasting time and money and resources. There's got to be another way to do this. Okay. So, they say calculate the maximum mass of the aluminium hydroxide that can be produced. First of all, let's just rewrite the balanced equation. It's quite complicated, but it's going to make life a little bit easier for us. So, we're going to rewrite the balanced equation, which was given to us. So, we have the aluminium sulfate. I'm not going to worry about the phases at this point because we're not dealing with gases. Okay, so I know I'm not going to have to do anything with volume. Yay, we like that. Okay, sodium hydroxide, which then goes to the aluminium hydroxide and the sodium sulfate. Now, they said to us that we have 700 grams. So I'm using 700 grams of the aluminium sulfate, and they want to know how much aluminium hydroxide I'm going to need. So it's just, there we go. So always important not to push the wrong buttons, grade 12s. All right, so we need to have the ratio, so it's 1 to 6 to 2 to 3, but actually only the 1 and the 2 are important because those are the ones we're working with, okay? And now we go, oof, this is not pretty because now we've got aluminium and we've got oxygen. Oh, that should be a 3. Okay, so what we need is we need to work out the number of moles of aluminium sulfate. Oh, that should be an N. Aluminium. There we go. Number of moles, aluminium sulfate equals M over M. That means we need the mass of aluminium sulfate. Right, so we know we're going to need to do M over M. That means we need to work out the molar mass. Okay, now, grade 12s, use your periodic table. Okay, so the molar mass of aluminium sulfate means I'm going to take 2 times the mass of aluminium, which is 27, plus 3 times the sulfate's mass. Sulfur is 32, oxygen is 16. Okay, it's 3 times the whole of that thing. So if we now look at this, and I'm going to quickly show you using the calculator, okay, so just to make it easier for you, so we're going to go 2 times 27 plus, now I'm going to put it in brackets, 32 plus 4 times 16 okay, equals 150. Okay? I've made a mistake, and I'm sure you're all looking at this and going, hang on, wait, Tracy, you made a mistake. Yes, I did. Because if we go back here, okay, let's just go back and do the replay. What needs to happen over here is this should be 3 times. Why? Because it's 3 times that. So now if we press equal, 342. Okay, it is a big number, which we actually did expect because it's aluminum sulfate. It's a big compound. Okay, so it's 342 grams per mole. It was 700 grams that we started with, so 342, which then gives me 2,05 moles. Not done yet. Question was, how much aluminium hydroxide would we get? Aluminium hydroxide is 2. Look at that. We'll just rub it out. 2. Aluminium sulfate is 1. So if I go back here and I now go, well, the number of moles of aluminium hydroxide, which is what I'm looking for next, is going to be the 2,05 times what I want, which is the 2, and the 1, which gives me 4,10 moles. Still not done. Question was, what mass would I get? So remember, mass equals number of moles times molar mass. Okay, so number of moles is 4,10. Molar mass, so I'm going to show you again, aluminium is 27 plus 3 times 16 plus 1, so it's 3 times 17. Okay, 27 plus 3 times 17 gives you 78, all right? And we get 319,8 grams. It is significantly smaller. Molar mass is significantly smaller. Okay, so it's what we expected. Do not get too worried about that, okay? It is what we expected. Please, grade 12s, the thing you are going to struggle with this is going to be getting the molar mass. Okay, so take it slowly. Make sure you use your periodic table. I don't know aluminium's mass off by heart. Okay, I know it looks like I do, but remember, I have this already prepared. I know I have it written down. I have it in front of me, so it makes it easier for me. Okay, but I had to go and look it up. You will need to go and look it up. Things like oxygen, hydrogen, sulfur, I use all the time. I do know those, but I've been teaching for a long time. Use your periodic table. Don't think that you know. Okay. Now, next question. So, still part of this whole water purification. The chemist now dissolves 0,85 moles of the sodium sulfate in 250 centimeters cubed of distilled water. He then tops it up with enough distilled water to make a 1 liter solution. Define in words the term concentration. This, like I said, those are one of the things where you go, really? 2 easy marks. Think about it. 2 marks out of 150, that's 10%? No, 1%? Doesn't sound like much, it's over 1%. But when there's 5 of these questions, that's 5 to 10% of your exam is going to be things like this. Make sure you know it. The term concentration means, okay, so we're looking at concentration. It is the amount of solute. Please don't say solid. Solute doesn't have to be a solid, okay? It's the thing that's being dissolved. It can be a gas and it can be a liquid, okay? But it's the amount of solute per cubic decimeter. And probably should say amount of solute dissolved per cubic decimeter. Cubic decimeter, remember, means decimeters cubed. 2 marks for essentially 7 words. Hey, easy, easy, easy. Okay? And remember, the unit we use is grams per centimeter cubed. Okay? Now they ask you, calculate the concentration of the sodium sulfate solution. All right, so now we look at this and we go, he dissolves 0,5 moles in 250 centimeters cubed, and then, not done, tops it up to make a 1 liter solution. Be careful, okay? Be very careful, grade 12s, because we look at this and we go, hang on, concentration, there's a couple of equations. Concentration is number of moles over volume. Concentration is mass over molar mass times volume. Not going to use mass over molar mass because we don't have mass. Silly. But I was told, if we look earlier, that the number of moles is 0.85. Okay, we've got part of this, but the problem becomes, okay, we know that this is 0.85. The question said he makes a solution, let's just look at it again, in 250 centimeters cubed of distilled water. Most of you stop reading at that point and go, okay, 250 centimeters cubed, divide by 1,000, gives me decimeters cubed. Off we go, nice and easy. But he then tops it up with enough distilled water to make a 1 liter solution. 1 liter solution. The volume is 1 liter. Okay? Volume is 1 liter, not 250 centimeters cubed. He makes the solution in the conical flask using 250 centimeters cubed and then adds more water to it. Guys, the volume is 1 liter, but concentration is in grams per decimeter cubed, or number of moles per decimeter cubed. I said grams per decimeter cubed. Actually, it's moles per decimeter cubed. Pretty sure someone was shouting at the TV. Well done. It's moles per decimeter cubed. So, how many decimeters cubed in a liter? 1. That's why they gave it to you. And that's 0.85 divided by 1. 0.85 moles per decimeter cubed. Be careful. Okay? The first time I looked at this question, I went, oh, 0.85 divided by 250 divided by 1,000 gives me a value. But then I left out half that last part of the question. Can you see why active reading is so important? Can you see why you have to make notes? This is why when you do it and you see me doing all this scribbling, that's not just because I'm explaining it to you. That's what you should be doing on your question paper. Okay, it's the sort of thing you should be doing, grade 12s. All right, now, we're going to take a short break, and then I need your thinking caps on this last question. It's quite a challenge. So I'm going to take a little break, because I need to get some water, get something to drink. I'll see you in a couple of minutes. Welcome back, grade 12s. Now, hope you got your thinking caps on. Grade 12s, we are still doing chemical calculations, but I want to show you how it can be integrated into your other sections, okay? That even though the last few questions that we've done have pretty much been standalone, that they didn't really relate to anything per se that you've done, this absolutely can happen. So let's look at this question, okay? We've adapted it from the exemplar paper from 2014, and it is adapted. We've made quite a few changes, but I want you to see. Sulfuric acid is used, amongst others, in the manufacturing of fertilizers. Fertilizers, very, very important section. Make sure you know fertilizers well. The flow diagram below shows how fertilizer D can be prepared using sulfuric acid as one of the reagents. Okay, so let's look at what we've got. I'm not even going to look at the question, okay? And this is how I would do any question like this, because we know, because this is a show on chemical calculations, it is going to be a chemical calculation. If you are reading this question in your exam, you don't know where they're going with it, okay? So first thing we're going to do is I go, okay, sulfur plus oxygen gives me compound A. So sulfur plus oxygen, compound A will be sulfur dioxide. Okay? It's the first part of the contact process. This whole point from here to here is the contact process. Okay? Then SO2 gets added to something, probably O2. Compound B will be SO3. So this would be oxygen. The SO3 then gets dissolved in sulfuric acid to give me H2S2O7. Okay, remember, we can't dilute that straight into water. Makes pyrosulfurous acid. Okay, too dangerous. Gives off lots of fumes, gets very, very hot, lots and lots and lots of issues. Then the sulfuric acid gets added to ammonia, which is NH3. That means fertilizer here would be ammonium from the ammonia, sulfate, and that would be NH4,2SO4. Okay. Ammonium sulfate. So, from this question, in an exam, they can ask me things like contact process, what's the name of the process. They can ask me, and they particularly do like to ask this, is the reaction between, remember, SO2 plus O2 gives me SO3. This is actually the reason why it's called the contact process, because we use vanadium pentoxide V2O5 as a contact catalyst. So I can now ask you, and it's reversible, so actually this reaction goes backwards and forwards, and here I can now ask you about how do I increase the yield of the SO3, what do I do to change the equilibrium. I can ask you Kc calculations, I can ask you how to increase the rates of the reaction, I can ask you what the conditions are, I think I've said that, I can ask you what the process of the vanadium pentoxide is. We can just go absolutely berserk on this question, okay? Lots and lots and lots and lots of things we can ask. So what we've done, though, is I've identified the compound. I've identified probably the most important reaction, which is from A to B, okay? Let's see what happens after that. Let's see what they ask us. So the first question is, right now, look at that. The name of the industrial process for the preparation of sulfuric acid. Brilliant, we just did that. It's the contact process. You have three important industrial processes: contact, Haber, which is ammonia, it's actually what we did right at the beginning, question 2, and Oswald, which is for nitric acid. Okay, make sure you know the names. Then they say to you, an impure sample of sulfur. In other words, even though I take the sulfur, put it onto a scale, I get 150 grams, it's not 150 grams of sulfur, it's impure. Okay, not all of it is sulfur, there's other stuff in there. Burns in excess pure oxygen, brilliant, to produce compound A, which is collected, brilliant, okay. Stored in a large cylinder which has a variable volume. Oh boy, life's starting to get interesting now, okay. At STP, STP stands for standard temperature and pressure, which means that it's 101,3 kilopascals, and 0 degrees Celsius, 0 Kelvin. I mean, can't be 0 Kelvin, that's minus 273. Not a chance, 273 Kelvin. Its volume is found to be 95,2 decimeters cubed. Why did they tell me at STP? Because right at the beginning, as part of the checklist, I said you must know that number of moles is volume divided by molar volume. Okay, molar volume is such an important concept. You would have learned about it in gases as well. Okay, so gas laws, we get in there. You all go, no. It's all right. Remember, 1 mole of any gas, regardless of its mass, at STP is 22,4 decimeters cubed. Okay, that is molar volume. Okay. We only use molar volume at STP, okay? The molar volume of a gas changes when temperature and pressure changes, okay? We are not going to consider that. Only at SDP, so molar volume 22,4 decimeters cubed. So straight away, by saying to me that the volume of compound A is 95,2, I know it's not 1 mole, because it's not 22,4, it's more than that. Okay, we can live with that. So now what do they say to us? Write a balanced chemical equation for the formation of compound A. Well, that's sulfur plus oxygen gives me sulfur dioxide. Yay! Very happy. Okay, now, determine the percentage purity of the sample. Okay, so sulfur plus oxygen. They said 150 grams of sulfur burns in excess of oxygen is not important. Okay. The volume of compound A, when we get to the end, is found to be 95,2. We now need to work backwards. In all the equations we've done so far, I've told you what the reactants were, and I wanted something to do with the products. Here, I'm going the other way around. So sulfur plus oxygen gives me sulfur dioxide. 1-to-1 ratio, we are so happy. Okay? What I'm going to do is if I can work out what mass of sulfur I need to create that volume of the gas, I can work out percentage purity. So stick with me, grade 12. So I'm going to start with the SO2 this time. Number of moles of SO2 is volume divided by molar volume. It was at STP, very specific. And if you can't remember that your molar volume is 22,4, it's okay. You have an information sheet. Okay, grade 12s, know your data sheet. Know that information sheet, okay? Use it. Don't try and remember things like this because you are just going to forget. And if you write it down wrong, if you write molar volume as 22,7, for example, they will not, there's no leeway for that because it's given to you. Be careful. Now, the volume they said to us was 95,2. The molar volume is 22,4. Okay, so when I look at this and I put it onto my calculator, watch, 95.2 divided by 22, not 222, that's just ridiculous. Okay. Or not. Let's try that again. Calculator didn't like that. 95.2 divided by 22.4. Remember, no fractions. Okay, we get 4,25. Write it as 4,25, please. Don't do all sorts of weird and wonderful things. Okay, 4,25 moles. Okay, so why do we like this question? I know some of you are going, we don't like this question, Tracy. I know you don't, it's okay. When I look at the number of moles of sulfur, it's a 1-to-1 ratio. So that means the number of moles of sulfur is also going to be 4,25 moles. You don't have to write that times 1/1, okay? That means I can now go, we want the mass of the sulfur. I'm sorry, this thing really doesn't like me today. There we go, let's try again. There we go. Okay, so mass of the sulfur. Yeah, you drew all the little green spots. Looks like it's got chicken pox. Okay, mass of the sulfur is going to be number of moles times molar mass. So it's 4,25 times 32, okay, from the periodic table, and we get 136 grams. But the question said that to get the 95,2 decimeters cubed volume, I had a 150 gram sample. According to this, I only needed 136 grams. So when I look at percentage purity, okay, because now this is what I want, percentage purity, this is like working out the percent of a test. Okay, so in other words, I have 136 out of 150. So if you got 136 out of 150 for your exam, which would be absolutely wonderful, that means you get 90,67%. So that sample of sulfur, only 90.67% is actually sulfur. The rest is impurities from the way it was mined, from how we got it, from the processes. It doesn't actually matter, okay, but it's never 100% pure. And in industry, that is exactly where some of the problems come in, because this becomes a problem in industry, in that the more impure your reactants, the less product you get. So that's why we have to have pure products. Okay, that's why making pure products is so important. Remember, this comes up in things like the aluminium, refining of aluminium, production of chlorine. I can remember in the production of chlorine, we can absolutely bring in something like this. So we can tell you, well, we should get 200 grams of chlorine. We only get 110. What is the percentage yield? Same as percentage purity. Okay, so they're very closely linked together. Okay, and the higher your percentage yield, higher percentage purity, the better you're going to get. The better your reactants are at the end, the more money you make. Okay, really, really important. Okay, so wasn't too bad. Great, now we move on. Now it says, let's see, we get down to the bottom. An analysis of compound C shows that this compound contains hydrogen, sulfur, and oxygen. Compound C has a molecular mass, or molar mass, of 1,78 grams per mole, and the following percentage composition. 1,12% hydrogen, 95.96% sulfur, and 62.92% oxygen. Find the empirical formula. All right, empirical. Empirical formula means the lowest ratio in which the atoms bond. Okay, empirical, lowest ratio. Okay, so for example, when it comes to, this is a little bit organic, I want to show you, methane, CH4, okay, or, no, that's a bad idea, let's look at your alkenes, okay. Your alkenes bond C and H to N, so CH2 is the empirical formula of any alkene, any. Its molecular formula is not that. It can be C2H4, C3H6, depends on the alkene. Okay, so empirical formula, lowest possible ratio in which the atoms combine. Lots of ways to do this, okay? So we're going to do this very easily. Percentages are great because percentages are numbers out of 100. So first step in this one is we are going to assume a 100-gram sample, because then what that means is that I have 1,12 grams of sulfur, 35.96 grams of, 1,12 grams of hydrogen, 35.96 grams of sulfur, and 62.92 grams of oxygen, okay? Very important. This is hydrogen as an element. This is oxygen as an element, not hydrogen gas, not oxygen gas. Do not use them as H2 and O2. Do not. You will get this wrong. Now they say to you, well, they don't say to you now, step 2. So we assume a 100-gram sample. We need to work out how many moles of each of these we have if this happens to be the number of grams. Now we do a 100-gram sample because the percentages work into grams, okay? So if we look at the number of moles of hydrogen, and remember number of moles is mass divided by molar mass, so it's 1,12 divided by 1,12 moles. We love calculations like that. Number of moles of sulfur, mass over molar mass, so it's 35.96, is 96, yes, 96, divided by 32. Now, I want you to see something, and I've done this, I want to show you on the calculator so you know I'm not joking this. 35.96 divided by 32, 1,12, okay? Don't get freaked out by that, okay? There's no reason why they can't be the same, so it's 1,12. Okay, so we've got 2. Let's do the oxygen, and I'm going to run out of space again. One day I'll learn. Okay, and this was 62,92 divided by 16, and we get 3,93 moles. That's fun. You like it? Okay, so what do we do with this, Tracy? Well, watch. Okay, we're looking for an empirical formula. Empirical formula means mole ratio. So I'm looking for the ratio of hydrogen to sulfur to oxygen. Hydrogen, we said we had 1,12. Sulfur was 1,12. And oxygen, 3,93. Okay? So, now we go fine. So, can we have half an atom? Of course not. Divide by the smallest number, which is the 1,12. So that's 1, 2, 1. Now watch. Okay, we're going to do this. Or not, because apparently this calculator really doesn't like me. Okay. And we get 3.5. Okay, we're okay with that. Still a problem, is it not? Because now I have 1, 1, and 3.5. I can't round that number up or down. 3.5 we leave as 3.5. But can I have half an atom? Of course not. Now dividing by 1 again makes no sense because I'm just going to keep getting 3.5. So let's multiply by 2. Okay, so this gives me 2, 2, 2, 2, 7. I need to get the smallest ratio of the atoms to each other as a whole number. Okay, as a whole number. It's really, really important here. Okay, it's got to be a whole number. So what does that mean? That means that when I write this as a formula, that means I have H2S2O7. Now let's go back to when we first looked at this. Didn't I tell you that compound C was H2S2O7? You've just worked it out again. Okay? You may or may not have to do that, grade 12s. Okay? But it's a check. Okay? At least now I can check myself and go, actually, that was right. Brilliant. Okay? So I know that it's H2S2O7. Okay? So that's the empirical formula. The question says, is verify if the molecular formula is the same. Prove. Don't assume, prove. How do we do this? We compare molar masses. We compare the mass. So, the molecular mass of H2S2O7, 2 times 1 for the hydrogen, 2 times 32 for the sulfur, and 7 times 16, okay? Now, I really want you to see that I'm not actually making these up, okay? So, 2 times 1 plus 2 times 30, plus 2, oh, wow, 2 times 32 plus 7 times, sometimes going slower is a very good idea. 178. Okay. It's 178 grams per mole. Okay, so what? Who cares? Well, look here. They said to me that the molecular mass is 178 grams per mole. In other words, if I take the molecular or the chemical formula, I should get 178 grams per mole. And look at that. I've got 178 grams per mole for the empirical formula. Okay, therefore, okay, empirical molar mass is equal to your molecular mass. Therefore, molecular formula and empirical formula are the same. I know you're writing a science exam, okay? Please just working out the molar mass is not enough. Okay? All right? So you got to the fact that it gave you the same mass. Explain your answer. Okay? That is where your mark allocation comes from. It's worth 3 marks. There's no way a 2-line equation is worth 3 marks, grade 12s. Please, 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 please be aware of that. Look at the mark allocation. And remember, okay, your mark allocation is quite mean. It's the only way I can put it. So a lot of times you have to do a lot of work for only 1 or 2 marks. It's not the other way around. In the past it used to be, so if you're using very old papers, you'll see that actually pretty much for everything you wrote down you got a mark. It's not the same, okay? We're only giving you marks for the final parts of a process or the final thought process, so please be careful here. 3 marks means I've got to actually have 3 things at least. One is the equation. One is telling me that the molecular mass is equal to the empirical formula mass. That means they're the same. Okay? Be very, very, very careful. Grade 12s. In light of this section, I know it's difficult. Okay? It is probably one of the most difficult sections you did in grade 11. Okay? And I know it's a section that you struggle with. The only way to overcome that struggle is to practice, practice, practice. You are going to get some sort of chemical calculation in your exam. Okay, and probably more than one. And I'm not including the equilibrium calculations in this, okay? Please, practice, practice, practice. Go back to your grade 11 work, take out those past papers, take out your grade 11 textbook, and do those questions over and over and over and over again. It is the only way to get this section into your head, okay? Will be in your exam, okay? Learn your definitions. Practice and grade 12s. Nothing more I can actually tell you, but practice, practice, practice. Good luck for your exams. Okay, I'm sure you'll do fine. Rewatch this lesson, get the notes, make sure you get them, and practice. I think I've said that a lot now, but it's the only way you're going to get through this. Okay, practice, practice, practice. And that is all I have for you today, so we will see you again next time.